Hello, this is a review of the GCSE Chemistry Chapter 1 Atomic Structure topic. It's really the start of the GCSE course. There's a lot of the fundamental principles that are included in here that are built on in later parts of the course. Now, if you're reviewing this as part of your revision and you've got the booklets from me, then you can simply double check and see that you're happy. If you're using it as a revision tool, I really recommend you pause on each task and then, after you've tried it, double check your answers and see how confident you can be in your knowledge and understanding of this topic area. So let's start with 1.1 atoms, and we've got here some basic keywords and the definitions. See if you can match them up. And let's take a look at the answers. So the atom is the smallest part of an element that would have all of its chemical properties. Straightforward definition. An element is something that's made up of only one type of atom. So lithium only contains lithium atoms, for example. A compound is made up of two or more types of atoms chemically joined. Now, the chemically joined is absolutely vital here, because it differentiates from the mixture. A mixture could be more than one type of atom or compound, and they are mixed, but they're not chemically joined. Now let's take the example. CO2 is carbon chemically combined with oxygen, so it's a compound. But carbon dioxide is also part of the air. It's not combined with the other gases in the air, nitrogen, oxygen, methane, argon. So that would be a mixture. Okay, next task. Just to get you thinking about some of the key ideas, see how you do with the true and false. And let's take a look at the answers. There are not 1,000 elements. There are just over 100. Few are still being discovered at the moment, but the numbers are not going to rise significantly. All substances are made of atoms. Elements are made of one type of atom. Compounds are made up of multiple types of atom. Compounds are listed on the periodic table. Absolutely false. The periodic table only tells us the elements. Sulfur is a compound. No, it is an element, and we can prove that by finding it on the periodic table. Sulfur, though, is an element, and that can be found on the periodic table, symbol Na. And finally, an element contains only one type of atom. As we've already discussed, that's true. Next task. This is about finding your way around the periodic table. I'll give you some examples in a second. Okay, 5 elements whose symbol is the first letter of the name. I've gone for the first 5 going from atomic number 1. So hydrogen, boron, carbon, nitrogen, oxygen, all have a symbol that is the first letter of that name. 5 letters whose symbol is the first 2 letters of the name. So I've taken the examples helium, lithium, beryllium, neon, and aluminium. There are others. When we're looking at elements whose symbol is 2 letters, but only the first letter matches, there's quite a few of these as well. I've gone for the first 5. They are magnesium, chlorine, chromium, manganese, and copper. And finally, it was elements that have got absolutely nothing to do with the name. The symbol seems totally unrelated. We've got sodium, which is Na from natrium, potassium, K from kalium, iron, Fe from ferrous, W is wolfram, but that's actually tungsten. The most interesting one, where we can still see links to this, lead's old name, the old original name is plumbum. Now, lead pipes used to be used to carry water, and we still have a little bit of a hangover from that when the lead pipes break, or when water pipes break, we call a plumber. Plumber. And we're seeing the root of that in the symbol of lead. We have to do this. We can't just give them the first letter. We've only got 26 letters, and we've got over 100 elements. So we need to be creative in giving them the symbols. A very basic introduction to structure of the atom here. Try this and see how you do. Okay, so purely based on this diagram, it tells us that there is a central nucleus and that electrons are outside the nucleus. We're going to develop that a lot more as we move on. Where we see the word nucleus elsewhere, we talk about it in cells, and it's the control centre. It determines cell operations. Now, actually, it's the protons within the nucleus that determine what element the atom is. So it is also a very important component. We're going to move on now to look at balancing equations, and we've got a worked example here. So H2 plus Cl2 goes to 2HCl. I've got to have the same number of hydrogens and chlorines on both the left and the right. When I balance an equation, I can only add big numbers. I can't change the formula. HCl is always HCl. Hydrogen always exists as an element as H2, just like water is always H2O. Second example here that's slightly more complicated. And then I'm going to recommend you have a go at these 10 examples, and then we will go through the answers. Okay, taking a look at the first one, you can see that we've got K3PO4 on the left, so I'm going to need 3 KOHs. And because I've got the 3 OHs there, well, I can also do it from the sodium. 3 sodium, so I need 3 NaOH, and when I check through the rest of them, the O's and the H's are balanced. I'm not going to go through all of these in great detail, but you can check them as you go through. So, number 2. Number 3. Number 4. On number 5, I'm looking at the NO3 in brackets, and I can see that I will therefore need 2 AgNO3. If I need 2 AgNO3, I will need 2 Ag. Going to carry on a little more quickly with a few more of them. So here's the answer to number 6. 7. 8. 9 is a slightly unusual one in the sense that it's already fully balanced. You don't need to do anything with it. And number 10, I'm looking here really to balance it at the lowest common denominator of the hydrogens, which of 2 and 3 is 6. So I would need 2 of the NH3s, 3 of the H2s, and that actually balances the N2 or the Ns as well. 10 more examples here. Going to let you work through them and then check the answers. Here's number 11. Number 12. For number 13, I am going to break it down slightly. I've got 3 SO4s on the right-hand side, so I'm going to need to add a 3 to the K2SO4 here. Now, because I've got 3 K2s, that means I need 6 KBRs. So I've got 6 potassiums on each side. And then, because I've got 6 BRs, I need 2 AlBr3s to balance them. Carrying on a little more quickly with the remainder now. Number 14. Number 15. 16. 17. 18, 19, and 20. And it might be worth pausing this if that's gone a little too quickly, just so you can double check that you've got to the answers that you need. Remember, there are marks available for balancing equations, but there will be marks that will be contingent on you balancing equations as well. So it's a really important fundamental skill to have. Moving on, we're going to take a look at the law of conservation of mass, have a go at these questions. And now let's take a look at the answers. So the law of conservation of mass is that the total mass of reactants is equal to the total mass of products. We are merely rearranging atoms, we're not creating anything new. So if I start with 100 grams of calcium carbonate and I heat it, I would expect there to be 100 grams of product. Now, when I actually weigh the product, there's only 56 grams. But if you take a look at the equation, there's a big clue as to why. Because we're making CO2 and it's a gas. Now, when we make a gas, we can't measure that on the balance. That's escaped into the air. So we can assume that the remainder, after the 56 grams that we've measured, which is 44 grams, is CO2, and that's escaped into the air. So let's take a look again, slightly different here. I started with 64 grams of copper, but actually after I heated it, I found it went to 80 grams. Look at the equation and try to determine why. And hopefully what you saw there is that this time we've taken O2 from the air and it's now trapped as part of the compound, part of the solid. So the mass appears to have gone up. This is a good comprehension task, so it's just about reading through, taking the time to find the answers and then putting them down on paper. So if you take a read through it and then have a go at the questions, and we'll have a look at the answers in a second. So question 1, what does the term ppm stand for? I've shown you where we can find that within the document, and there's the answer, parts per million. What does the word desalination mean? Well, again, highlighted within the box, but we are removing salt from seawater. Part 3, who was the first person? Aristotle. Number 4, the ratio. So we're told content of 35,000 parts per million in seawater and less than 1,000 in fresh water. So the ratio is 35:1. And then finally, how distillation can be used. It actually goes into quite a lot of detail here about vacuum distillation, but in simple terms, distillation is evaporation followed by condensation of the liquid. Now we have a missing word task to take you through some of the key words related to separating mixtures, something that you'll hopefully be familiar with also from Key Stage 3. So these are anagrams, have a go at them, and then we will review the answers. So, salt is a solid which dissolves in water. Salt water is a solution. We can see through salt water. A word to describe this is clear. So some really quite straightforward words in here as well. Solids like salt, which dissolve in water, are soluble. Chalk does not dissolve in water, which makes it insoluble. When you mix chalk with water, the liquid will turn cloudy, which is a sign that it's insoluble. And when you mix sugar with water, the sugar is the solute and the water is the solvent. The solute dissolves in the solvent. More missing words. Have a go. And the name of a soluble solid, we've got sugar in there. A word which means the same as transparent, clear. A word that could describe orange squash, that would be a solution. And the name of a solvent, and we've gone for water. Moving on to the next task, have a go at identifying whether these are elements, mixtures, or compounds. Now it says here to try to give a reason why, and I will talk about that as we go through. So A and E are elements. We know that because they're made up of only one type of atom. So that takes us back to the definition from earlier in the video. We've got B, C and F are compounds. They are made of more than one type of atom and they are chemically combined. And then that leaves us with D, which is a mixture. And that's more than one type of atom here, but it could be more than one type of atom or compound. And they are mixed together, but they're not chemically combined. More questions here. And now let's review the answers. So 5 gases named in the passage. Identify them, state whether they are elements and compounds. Well, I've highlighted them as well. The one that stands out here is water. We often think of water as a liquid, but it does state very clearly here that it's water vapour. And there is water vapour as a gas in the air around us. If I then separate these out, the top 3 of these are elements and the bottom 2 are compounds. One type of atom in the elements and more than one type of atom chemically combined in the compounds. Drawing out for number 3 a gas that exists as single atoms, I've gone for argon and we can see the diagram there. If I then consider one that is diatomic, 2 atoms chemically combined, that could be nitrogen or it could be oxygen. Still a gas, they're still spread out, but they are in pairs. And finally, a compound could be CO2, it could be H2O, but it looks like this. Moving on now to chromatography, and it's handy to know the details of this method. There are some questions to answer, and I have put some dots onto the chromatography paper so that you can answer the questions. So work your way through how many different dyes in each food colouring to start, then the rest, and we'll review the answers in a moment. So how many different dyes? Well, 3 in the first, 1 in the second and third, and 2 in the fourth. And we know that because we're simply counting the number of dots where the ink is separated out into them. Number 2, why do we draw the line in pencil? Well, if I use a pen, that's ink, and that ink would then dissolve in the water and be carried up the paper. It would become a part of the chromatogram. Why were the spots labelled? Really straightforward. It's so that we know what ink is what, so we don't have to remember it. For number 4, why is the chromatography paper hung with the bottom in the water? Well, we need the water to soak up the paper and carry the ink with it. Why must the water level in the beaker be below the spots? Well, otherwise the ink would dissolve directly in the water. And finally, why are we going to wait until the water is near the top of the paper before taking it out to dry? And that's because we want the inks to be as far apart as they can possibly be. That takes us to the end of part 1 of chapter 1, Atomic Structure. And I recommend, if you're happy with this, you follow on to look at part 2 as well, which will go into a little bit more detail on, for example, the formation of ions. Thank you very much for listening.